Here we go, recording now. Okay, so yeah, I hope this morning was useful for you. It's a bit of a rapid tour through OR and data science, mainly to give you a sense of some of the possibilities and some of the things you'll need to consider when undertaking a modelling project. So hopefully it's led off lots of interesting ideas. And I have to say, browsing through the chats you've been having in your peer support groups, fantastic ideas for projects coming up. Really good ideas. So do absolutely run with those, because there's some great stuff coming up here. So fantastic, and also some great ideas to collaborate as well, which is fantastic from our perspective. I think that'd be brilliant if we get some great collaborative projects going as well. So this morning we've primarily talked about OR and data science and what those things were, and some of the methods and some things you need to consider. Now, a lot of the methods we will teach you, because we now use sort of free and open source solutions for all of the stuff we do, a lot of what we do now is programming based. So a lot of things we are based in either Python or R. Most of us using Python, but also R for some stuff. And so we thought, so when we've run this before, sorry, can I just make sure everybody is muted, because I'm getting some feedback and so on, unless it's me. But when we've run this before, we found that we've dived quite rapidly into the programming stuff without really talking about some of the principles behind programming. And so I know some of you do have some programming experience, and hopefully this will be relatively straightforward for you, although you may learn some new things as well. But we are going in with the assumption that you don't really know much about programming, or you haven't really done much or any before. So we're going to talk to you about programming from first principles and what these concepts mean. So we're not actually going to do any coding this afternoon. That will come on Tuesday, but taking you through sort of the basic concepts. So I'd like to first of all give thanks to my programming tutor when I was 4 years old. I think I posted in the Slack a few days ago that my first experience of programming was when I was 4, back in 1985. I received my very first computer, an Atari 800 XL with a whopping 64 kilobytes of memory, and it was fantastic to see so many of us competing on who had the least memory back in the old days, which was quite amusing. But yeah, 64K was quite a lot back then. Now it's your schedule for this session is nearly as big as that, just the PDF file. So just to put that in context about how much memory we're talking about. One of the fantastic things that came with that computer was a cassette tape called An Invitation to Programming. And it took you through the basic concepts of programming, right through from concepts as variables and conditional logic to actually getting you to write a program. And that has always stuck with me, and very much the programming training that I'm going to be delivering to you both this afternoon and over the next 3 weeks is very much inspired by that. Now, you don't have the stress and worry of only being able to play with 64 kilobytes of memory. You don't have to worry about getting an input from the user and limiting the number of characters they can type in, because you may not have space for it in the memory. But nonetheless, the principles remain very similar to what they were so many years ago. So anybody that played around with programming back in the day, those of us a little bit older, you may well reminisce about some of this stuff. So what is programming? Well, essentially, computers carry out instructions that are given to them by the user. Computers are inherently stupid. You have to tell them what to do. And the instructions are essentially a series of steps that the computer will work its way through. Now, programming languages are the communication medium that allow us to talk to the computer to provide it with those instructions. And then we can write computer programs that essentially bundle up lots of these instructions, and then these instructions get executed when the program is run. So we can write a program that does a certain thing. It's got lots of instructions to tell it to do this, this, and this. And then we run the program and the computer will carry out those instructions. Now, if we just think a little bit about the architecture of a computer. So essentially a computer architecture is made up of one or more input devices. Those are things like, your keyboard, your mouse, the swanky new tablet I've bought, the graphics tablet, whatever you use in order to be able to provide input in some way to your computer. And these input devices are used by the user to issue instructions. You've also got your central processing unit, or CPU. That's the main processor that interprets the instructions and executes them. So that's doing a lot of the heavy lifting. The actual stuff that you're instructing it to do is done in the central processing unit. We also need memory, and we need memory for two reasons. We need memory in order to store information that may be required later, either in the short term. So for example, we may store something, a number in memory or whatever it may be, so we can come back to it in a moment. But we may then, after the program is run or after we turn our computer off, that disappears from memory. We don't need it anymore. That's stored in RAM, so that's random access memory. Or we may need information stored longer term after the computer's been shut down, after the program has finished running, and that's your storage, such as your hard drive, for example. So in addition to all that, you also need one or more output devices. These are things like monitors, speakers, etc., that are used to communicate the outputs of the instructions to the user. Now, I'm sure most of you are familiar with most of this, but it's worth just thinking about what it actually means in terms of us passing instructions via a computer program to a computer. Now, there are two broad types of programming languages, known as low-level programming languages and high-level programming languages. So low-level programming language, such as assembly language, is it's unique to the architecture of the computer. So what you're actually doing is you're in a low-level language like that, you're giving it specific low-level instructions that tell the processor exactly what to do at the level of the processor. So it's specific to that type of processor, and you're giving it that processor level instructions. Now, that means it's very, very difficult to do, because you're not dealing. So for example, let's say you wanted to add the numbers 2 and 2 together. If anybody ever wants to try doing that in assembly language, I challenge you to do it. I had it as a task when I was doing my degree, and it is ridiculously complicated, because you have to worry about processor stacks and where various bits of numbers that are represented in binary form are being moved around. It's I'm sure some people like it, but it's not for me. But most of the time when we talk about programming, certainly in the modern day, we talk of high-level programming languages. And these are languages which strongly abstract from the details of the computer. And they use kind of natural language. So we can code in something that is readable and understandable to most people. And then the computer will then process those instructions, convert them down into that low level, so that the processor gets the instructions it needs in the format it needs and carries out those instructions. So examples of high-level programming languages, things like BASIC back in the old days, C, C++, C#, Java, Python, lots more. There's loads of programming languages out there. And they're the kind of programming languages, I'm sure you'll be delighted to hear, that we'll be talking about in this course. A key concept within programming is the concept of a variable. So we've already said that when you're programming, you often need to store pieces of information for later use. And where we need to store it just for in memory, in the RAM, where we need to come back to it later in the program potentially, we store it in something called a variable. And the best way to think about variables is to think of them as boxes that store information, and each variable has a name and a value. So the name essentially represents the thing that's being stored in that box, and the value is the thing itself. So we might have a variable called name, and that might store the value Dan. We might have a variable called age, and that might store the value 39. We might have a variable called employee, and that might store the value true. So we have a name for the variable, which essentially declares what it's storing, and then the value for that. And variables are enormously important in programming. You will be using them all the time for any computer program that you do. You're constantly storing pieces of information and then using them and manipulating them and passing them around and doing all sorts, as you will soon see. Now, because of this, there are lots and lots of different types of variables, because as you can appreciate, information itself comes in all sorts of different shapes and flavors. So we've got number type variables, and within that we've got things like integers. So integers are just whole number of variable values. We've got floating point numbers. Those are basically numbers with a decimal place. We've got text type variables. So we've got things like characters, which are individual letters, numbers, and symbols. And we've got strings, which are sequences of letters, numbers, and symbols. And integers, strings, and floating point, particularly integers and strings, you will use a lot when you first start out programming. Numbers and words and letters and sentences will be used a lot. Another one that's commonly used for conditional logic in particular is something called a Boolean. And this is a data type that indicates if something is true or false. It just takes one of those two values. And that's really useful because when we go on to the conditional logic, we can check to see if something is true or not, and then do something different depending on the value of that variable. We've also got things called collections. And within collections, we've got things like lists. Lists are ordered sequences of things. We've got sets, which are unordered sequences, so the order doesn't matter, but they're unique, so you can't have duplicates in there. We've got things called dictionaries, which are also unordered. The order doesn't matter, but they're pairs of index and value. So you have things like name and then a value for that. And tuples, which are like lists, but they can never change, they're immutable. And we'll talk more about all of these things in relation to Python when we come on to the Python training on Tuesday. So let's say we wanted to build a really simple program that was a simple calculator that just adds up two numbers. So in programming, what we would need to do is to first of all tell the computer to ask the user for the first number. Then we would store that number in memory as a variable. Then we would ask the user for the second number, and then we would store that second number in memory as a variable. Now we've got those two numbers stored in memory, in variables, what we can do is to perform an addition operation on the two variable values. So we can say, I've got a variable called first number and a variable called second number. I can tell it add first number to second number. Then we can store the result of that calculation as a variable, and then we display the result variable to the user. So really simple example, but that just takes you through the kind of process you need to be thinking about whenever you're doing any programming. Now, I mentioned a moment ago something called conditional logic. It's very rare that the programs that we write are completely linear. Often, we need to do different things depending on whether certain things are true or not. And this is known as conditional logic. That's all it basically means. It's the way of telling the computer, you may need to do this or you may need to do that. And that will depend on whether this thing is true or not. Okay. And if you think about it, real world systems are all like that. Not everybody that goes into an ED follows exactly the same process. Different things happen depending on different things, their urgency, what their condition is, whether they need to be admitted or discharged. They will go through different parts of the process. So conditional logic is enormously important. You will rarely get a useful computer program that doesn't have at least some form of conditional logic within it. So a good way to think about conditional logic is as a decision tree. So let's take this one, for example. Let's imagine I'm asking the question, am I hungry? If I'm not hungry, sorry, if I am hungry, then I'm going to ask the question, do I have cake? If I'm not hungry, then I'll do nothing. So if I am hungry, I also want to know, do I have cake? If I do, then I will eat some cake. If not, well, is the shop open? If it is, then I'll buy some cake. If it's not, I'll eat something else, or I would probably find another shop that does have cake. But that's just me. But essentially, you're thinking about your decision structure in that way. So visualizing conditional logic in that sort of decision tree framework can be really useful, because that's essentially what you're going to replicate in your computer program. And it might be sometimes we have more than a binary check to make. It may not just be as simple as if this, do this, if that, do that. It may be that we say, okay, well, how many cakes do I have? If I've got 10 or more, then I'm probably good for cake for a minute, so I'll do nothing. But if that's not true, then I actually want to check some more information. I want to say, well, if it's not true, but if I've got at least 5 of cakes, you know, that's probably the point at which you want to add something to your shopping list. If I've got fewer than 5, but I've at least got a cake, I've got a cake in my back pocket, I'll walk over to the shop. Otherwise, I'm in the situation where there's no cake, and that's going to take a nice run to the shop. So lots of different checks, and very often when we do real world conditional logic, those are the kinds of structures that we would use. Another common concept that comes up in a lot of programming, so like conditional logic, this is also something that you would struggle to write a meaningful program without including, is the concept of a loop, because very often we need the computer to do the same thing a number of times, and it might be that we need to do it a certain number of times, or it might be that we want it to keep on doing this thing whilst a certain condition is true. And we use 2 different types of loops depending on which of the above it applies. So for the first sort, where we want to do the same thing for a given number of iterations, we use something called a for loop. So we say, for this amount of iterations, do this. And for the second scenario, where we want to keep doing something whilst a certain condition is true, we use something called a while loop. We say, while this is true, keep doing this, essentially until it becomes not true. So let's look at a couple of examples. Let's say we want the computer to add 2 sugars to our cup of tea. So we would use a for loop here. We'd say to basically count the spoons of sugar, often including 2. The first thing the computer would do is say, right, how many sugars have I added? Well, the first time around this loop, it hasn't added any. So if it's fewer than 2, it will then put the spoon into the sugar, scoop, add to the tea, and then it'll ask the question again, how many sugars have I added now? So now we've got 1 sugar that's been added. Again, it's still fewer than 2. So again, in goes the spoon, we scoop, we add to tea, and again, we ask the question, how many sugars have I added? This time it's 2, so the loop stops. So it goes around and adds the sugar for the number of times we specified. And of course, we could easily expand that out and adapt it to essentially ask the user how many spoonfuls of sugar they want. So rather than saying, do this twice, we could get the computer to say, well, how many sugars do you want? We then store that answer in a variable, in this case I've called it X, and then essentially we do exactly the same things, only this time we're telling the for loop to go around this loop X number of times. So if the user wants 27 sugars, well, they'll have a very sweet tea, but they'll also go around this loop 27 times. So the other kind of loop we said is a while loop. So let's imagine we wanted our computer to sing to us while we fall asleep. Probably not advisable. So essentially what we would do there is to say, okay, well, while the user is awake, keep going around this loop. So the first thing it'll ask is the user awake? Well, presumably they're awake at the start. So that's why we've entered into the loop. So we'll clear our throat, sing for a minute, and then hit them over the head. If the user's still awake, then we'll keep going around that loop until the user's no longer awake, at which point we stop. So that's the difference between a for loop and a while loop. One essentially goes around a certain number of times, whether that's preset or defined in a variable. And a while loop says keep doing this until a certain condition is met. Okay, that's a sort of broad, brief introduction to some of the core concepts in programming. So what I want you to do in your groups is to start thinking in a programming kind of way. So let's imagine that Chalk Showers and Baths, division of Chalk Technology, Building a Brighter Future, has approached you and they've asked you to develop software for a new automated shower system, the Chalk Automated Shower with Genius Responses and Banter cash grab system. So in this new system, the user steps into the shower and the shower asks them for their name. It then greets them with their name, saying either good morning, good afternoon, good evening, etc., depending on the time of day. It then waits for the user to say begin, at which point the shower will turn on at 30 degrees C. Now the shower, once this happens, will continue to raise the water temperature by 2 degrees C every 5 seconds. If the user at any point says too warm, the shower will drop the temperature by 1 degree C, and it'll keep on doing that every 5 seconds. If the user says too cold, the shower will again start raising the temperature by 2 degrees C every 5 seconds. When the user says perfect, the shower will hold the current temperature, and it'll do so until the shower is finished. And it'll record it in a variable called perfect temp, alongside the user's name in a variable called username, and it'll store both of these things in a list called user preferences. So the shower will record their perfect temperature and their name, so we know what that user's perfect temperature is. The shower will continue to run until the user says end shower, at which point the shower says goodbye, followed by whatever their name is. The user presumably is slightly concerned about why the shower is talking to them, nonetheless. So what I want you to do, in your groups, you have 45 minutes. I want you to draw up an outline of this system. Specifically, you should draw some sort of diagram outlining how the system will work, including any conditional logic, loops, and variable storage. And I want you also to write a list of the variables that will be used in the system, along with the type of each variable. So remember we talked about the variable types, so consult back in the slide notes. And alongside each variable, I want you to write a short single sentence or so description of what the variable is storing. Now you can do this in all sorts of ways, and I don't mind how you do it, but essentially we want some sort of pictorial representation of the system if we were creating a computer program for this system. Okay, so important things to flag up: where the conditional logic is, where the loops are, where the variable storage is, and then writing all your variables out and what type they are and what they are doing. Any questions about any of that? No, good. Okay, so what we'll do, we'll see. Well, actually, we're running 3 minutes ahead of time. Makes a nice change. So you've got till 2:45 to do that, and I believe I scheduled in a comfort break as well. Yeah, so we will resume at 5 to 3. So make sure you take a 10-minute comfort break at some point within that, but work within your groups. Again, you may want to, I mean, the Jamboard stuff looks fantastic, so that could be a really good way. And if those groups who didn't use that, if you're very happy to, those groups that are, if you're happy to sort of just share the links to that, I think people will be very, very interested to use that. Do whatever works for you within your groups, and we'll resume back here at 5 to 3. And I'm at that point, I will be picking on some groups to present their diagrams and talk us through their system. Okay, fantastic. See you shortly.